glaciers are so important for us in India. What I shall be talking today about is the remote sensing of snow and ice, which essentially also involves the glaciers as well as the seasonal snow. How many of you have a little bit understanding about the remote sensing? Can you raise your hands? Okay, almost everybody has an understanding. And how many of you have a little bit understanding about the snow and glaciers? Okay, there are a few. So it means now I know where I should give the emphasis and what I should be talking about to you about things. So let us start first the understanding about the what's wrong? Okay, so so how do you look into the city? If many of you have gone to the mountains, particularly during winter time, and lived enough into the mountains during summertime, you would have definitely seen the snow. And it must be, so many of you are quite it looks very fine when you look through your naked eyes. And the important question, if you really want to understand how to use the remote sensing, first thing you need to understand why it looks white. And that we will explore a little bit. And why it looks white to the human eye? Because human eyes normally look into the visible region of the electromagnetic spectrum. And many of you are now familiar with remote sensing techniques. We do not only use the visible region of the electromagnetic spectrum, but we also use other regions of spectrum, such as near-infrared, thermal, or matter, whichever you want. Of course, in this lecture, I will not explore all those aspects, but we will try to concentrate some of the fundamental issues and how to apply those to identification and mapping of seasonal weather. The first key question which we need to understand is what it looks like to the human eyes and how it looks like when you move away from the visible region of electromagnetic spectrum towards the near infrared. And you can also see how the glaciers look like, and this adds the complexity to what you are going to do in future. So just I want to bring you to the, so you can see here you have a huge peaks over here, which is the GANGOTRI region, and on the peak only you have the snow, and the other regions looks like it doesn't have snow, or you have bottom down here is the ice, which is below, but on top of it is significantly covered by the debris. We will explore the issue later on, but you have a lot of complexity involved in it, and you can see that a certain region which you are looking at it is exposed to the sun, another region is in shadow. So what it really means that if you are looking from the satellite, some region will look dry, some region will look relatively less dry, or in the dark. So how we are going to handle the issue? We will try to explore this thing in subsequent chapters. Right. But let us start fundamentally understanding what is the difference between the snow and ice. It is very simple. So what really happens? Snow is the porous and permeable aggregate of ice crystal. So you have one ice crystal, you have another ice crystal, they come together, and then thousands and millions of ice crystals come together, and in between each ice crystal there is air, which is trapped in between that. So you have a porous aggregate of ice crystal, then you have snow, and it has generally very less intensity. We will explore that later on. When the interconnecting air, because you have two ice crystals where interconnecting air is removed from it because of the compaction or various other phenomena. And then when it is removed, and that is normally called as spin off, or a process known as overflows outside, and because of the compaction, air particles they trap between that escapes into the atmosphere, and its density is significantly increased. And when it increases around 900 kilograms per cubic meter, then you have ice which is formed. Now, when that ice gets converted into the glaciers, which is also a very important thing, because glaciers, in order to convert this ice into glaciers, you have to have sufficient large mass of ice. And if there is sufficient large mass of ice, because of the gravity, it will start moving, or it can also move because of the creeping. That is, the wave itself is moving on the slope, it starts deforming, and the deformation creates the creeping, and that is the moment it starts moving, then ice is formed. However, you want to differentiate ice, which is on the land, which is called a glacier, from iceberg, and therefore there are some other conditionalities added into it. That means it should be formed due to metamorphism and recrystallization of naturally fallen snow on land surface of the earth. So that no one can say that the floating ice in the ocean is a glacier, and essentially glaciers will have ice, snow, water, and everything. We will explore this in much detail and subsequently in my lecture, but this is important for you to understand the differences between these, and you can see what really happens when snow falls. And the snow, even in the fresh snow, and which are very dry and calm conditions, because many times they become extremely windy, and if it is not there, if the temperature is reasonably below, because snowfall normally takes around 0 degrees Celsius, but it can also have slightly more. So you have a fallen under dry and calm condition, then it will have around 50 to 70 kg per meter cube in the density of the snow, so which is very fast snow, and it doesn't have very large density. But at the same time, the temperature is reasonably higher, which is very close to 0 or +1 or something like that. Then you have a direct snow. That means it actually added ice crystals are formed into the atmosphere. As they start falling, some of them start melting. And before they are not completely melted by the time it landed on the land, then it becomes a dam. And what is that? The water has a significantly higher density than snow, and suddenly the density becomes very higher. You must be wondering why we are discussing about density, because the density tells you how much glacier store water is there, as well as it defines the numerous reflectance properties of the snow. So we will visit that, and that influences your ability to delineate snow by using satellite images. Therefore, it is important to look into that. What will happen is, it is altogether different ballgame. When the snow is falling, and when it comes down, it falls on the land. The moment it falls on the land, the very different metamorphic processes start taking place, and snow dramatically changes, and there is no other object on the earth which dramatically changes on its landing on the earth's surface like snow. So what happens to that when the snow is fallen and it gets accumulated on the surface? Its crystal structure starts changing, and its density starts increasing. And then it goes up to around 200 to 200 kilograms per meter cube, and then we will try to avoid that in order with other processes. But another important question is wind back snow. What really happens is, when the snow, once it is fallen, during and the time of the snow falling, there could be wind. And even after snowfall is over, suddenly the huge winds start flowing. And because of the huge movement of wind, snow also gets redistributed. So that means many of you have seen there is a whitening phenomenon, and anytime if you have gone to the mountain and suddenly you realize that there is a whitening, that means everywhere it looks white, nothing is there. Because of the wind, snow is moving along with the wave into the atmosphere. And when it falls down, because of the energy which is by force by which it is putting, its density also goes. Another critical question is the fur. That means the fur is an intermediate process to convert snow into the ice. So what will happen, you can see that there is a huge difference between the fresh snow and the glacial ice. So this is not going to happen overnight. This is going to happen over a period of time, depending upon which part of Earth you are. If you are in Antarctica, this process may take 100 years. And if you are in Himalaya, this process can take place in a couple of years. And why there is so much difference, we will look into that. But this is an important thing for us to I don't know whether we can. Huh? Yes, sir. Where is that? Okay, third. Okay. Okay, good. Thanks. And the next is when it gets converted into ice, and when it gets converted, that means most of the air which is trapped between the ice crystals is completely removed. There could be various processes by which it gets removed. Either it is because of this. Because of the melting and refreezing, or it is because of the compaction, whatever it is the metamorphic process, which is called metamorphic process. Once it is completely removed, then the glacier ice is formed, and the ice which has very high density, around 900 kilogram per meter. So this is for you to important to understand, because as snow changes, fresh snow, which is a lot of air trapped in between, to glacial ice, there is a substantial air is removed. It is changing density, and in between is the snow and fur, where it is couple of 1 year old by technically, but it is very tight, it has a lot of water in it, and it has a very high density. This phase is very important as we move towards the application of remote sensing into the glaciology. So what really happens, I was saying that there is a small nucleation around a dust particle takes place. Actually, it can be around dust particle, or it would be also because of the freezing of the water molecule. So you have, and then it grows in a hexagonal prism, and the simple plate unstable crystal grows larger and arms sprout, and at the end of this, in the atmosphere, you have a beautiful structure of the snow. So it is called because of the difference in temperature, and it slowly grows into the atmosphere, and it has very complex structure like this it grows, and you know that by any standard, this complex structure is unstable and it has to get rounded eventually. So what really happens once it is fallen onto the land, this is called as snow metamorphosis. That means that the crystal, which is very complex and hexagonal in nature, cannot maintain as it is, as it fallen on the land, and it starts tend to become more and more round, and the snowpack is in a constant state of change, and this change is known as metamorphism. So what really happens? That metamorphism takes place essentially because if you look into the mountains has very peculiar phenomena, a very peculiar thing. The mountains say snow very greatly, even over a short distance. What it means is that if suppose snow is falling, it is not falling, even if it is falling equally, it gets redistributed on the land. Essentially because if you have a steep slope, then snow will not be able to stick to the steep slope. It will come down either in the form of avalanches or some other reason, and it gets accumulated in small region. When the snow is fallen because of the wind, it is going to get redistributed as a region which is the leeward or windward, depending upon which side of wind you are, it can get accumulated more at some places. So you have a huge variation in snow depth, and which is also causing significant amount of different metamorphic process. Snow density varies from layer to layer, from 50 to 400 there are features. What really happens is you have different events of snowfall. That all season snowfall is not going to fall within 1 day or 2 days. You are going to have snowfall now. After 15 days you can have another. After 15 days you can have another snowfall. So what really happens is once you have one snowfall of this time, intervening period there may be slightly rise in temperature, and if there is a rise in temperature, snow will melt. And if the snow melts, then on the surface the water is generated, liquid water is generated, and the liquid water penetrates through the snowpack, and since the snowpack temperature is below the freezing, the water also replaces. And because of that, the density of snowpack goes up. So, and then, therefore, you have a snowpack which has very high density, and then again, there is a fresh snow falls on it. So you have two layers, the top layer which has very low density and bottom layer which has a very high density. And that creates very different structure and which is conducive for the avalanches and others. So, snow grains from different layers varying size and shape, we discuss about it. Air in pore space is saturated, that means 100% of relative humidity is there, because as we are discussing that in between two ice crystals, there is air. And that air is completely saturated, and it depends upon the temperature. If you know that, it is a distinct relationship between how much will be vapor pressure will depend upon how much is the temperature. So it is related to the warmer pore spaces hold more water vapor than the cold pore spaces. So I am sure many of you have a couple of lectures which is given here, we would have talked about the relationship between the water vapor and temperature. So I will not elaborate more on this issue. And then another key issue which changes snow very dramatically because of the snow temperature is generally warmer close to ground and near 0 degrees Celsius, and because polar snow is a good incident. What it means? It means is you have now geothermal energy coming from the ground, and you have a thick bag of snow, and you have atmospheric temperature which is very cold, maybe -10, -15 degrees Celsius. But the intervening ice or snow, which are intervening air masses, is good insulator. That means the whatever lower temperature is on the air, it doesn't get down, percolated to the bottom. So what happens is the bottom of snowpack is at 0 degrees Celsius, and the top layer continues to be -15, -20, depending upon our atmospheric temperature in the coast during peak winter time. And what it creates is, it creates very different unstable temperature conditions. And if you have a bottom which is 0 degrees Celsius, top which is -10 degrees Celsius, you start the energy flow, or temperature flow, energy starts flowing bottom to top, and this is creating a different kinds of metamorphic process. We will not go into detail because normally I reserve these lectures for a special course which you will have, but you should understand. So, this is what Precisely says. So, all these conditions makes it necessary for snow to change, and it goes through the process of metamorphism, and the end of that metamorphism is the conversion of snow into the ice. But the main thing will happen in between that, and it will lead to the formation of avalanches, it leads to the snow melt during summertime, which will provide water in your rivers. So all those things are going to happen in the intervening period. So what I was talking about is that why these processes are important for us to understand. And these are important because changes in grain size and liquid water content is important parameter for avalanche forecasting. So if you really want to know it, because India has a huge army which is in the northern part of India, in a higher Siachen glacier or very high altitude, so one of the key things which they need is avalanches forecasting. That means so that they can move safely into the mountains. So this is a very key parameter that how snow is going to change, because I was talking to you earlier that you have a one layer a bottom layer which has, because of it has fallen earlier, it has high density, and top layer has a low density, and the surface between these two is now prone for sliding. And so you, depending upon the slope, you can forecast how much load it can get. So you can say that if there is a 10 millimeter of snowfall, then there is a possibility of avalanche in this region. You got that idea? Huh? How many of you have not got this idea? Wonderful, everybody got it. So, nice. So, this is what happens. Another key parameter, if you want to know, in a melting, because snow starts melting and introduces water to our river system, is albedo. Albedo is an important parameter to assess snow refractive. So this is very important parameter in avalanches, as well as also important parameter in snow melt runoff. Because amount of wind will depend upon how much energy, solar energy absorbed by the snow. And the absorption depends upon the albedo of snow. And because of that, this is an important parameter for us to understand. And it is necessary for us to understand snow metamorphic processes, because this will give us linkages between snow metamorphism, state of snow, and its detection by using remote sensing. Correct? So we will use towards that I am giving you this idea again. So what is key parameter? If you have a visible band of electromagnetic spectrum, then what determines the reflective snow? Or when solar radiation comes, key parameter is refractive index. Right? How many of you know the refractive index, meaning of refractive index? Tell me.
The ratio between the velocity of light in the
basically just how
Yes. Tell me. Tell me. Okay. All right. Go ahead. Okay, I won't tell you that right now. Little bit. Some of you have said that, some of you will need to real to that. But there are two parts of refractive index. One part is a real part and another is imaginary part. What imaginary part means? Little there, but it's absorption. So what it really means is that what really happens? If you really want to say what will be the albedo of the snow, we need to understand these two processes. One process is how snow, when the solar radiation penetrates into the ice crystal, what happens to that? And how much it gets absorbed and how it gets refracted from there. So these are the, and if you really look into that, you can see here the wavelength is 0.5. Which part of spectrum is the human eye is sensitive? Visible? Which is visible? Good. Nice. So you have a visible part of the electromagnetic spectrum, and why that part of spectrum is very important. Definitely not because we can see, but something else is also there.
that is absorbed by us.
70% of the solar in the band.
So what you really look into that is the peak of incoming solar radiation is in visible band of spectrum. What means the most of the energy which is coming from the sun is coming into the visible part of the electromagnetic spectrum, and it has, then what happens in that spectrum it predominantly determines how snow is going to melt, how it is going to metamorphose, how much water is generated. So for us, this is spectrum of electromagnetic is very important. And if you can see here that what really happens is there is no huge, you can see here this is ice, which is the real part of spectrum, and you can see here there is no huge difference as you move from wavelength which is around 0.5 to 2.5, there is a small, which is only 0.125. to 0.135. So it's very small difference in refractive index. As well as there is not huge difference when it is converted into the water. This is very important for you to understand because sometimes the pore space, which is the air, if it is melting, will be taken over by water. So if there is a large difference in the refractive index between this ice and water, we could have a great potential to use visible band spectrum to know the state of snow. But that opportunity is not there because we do not have significant change in the refractive index. If we do not have significant difference in refractive index, and if you look into the real part of refractive index, as well as look into the imaginary part of refractive index, that means the absorption. And if you see your visible part of region, there is no huge difference between ice and water. Correct? It's very close. Not invisible. So when you look by ourselves, you know the flow looks very white. And you know how water looks like. Why is that? Now both have no absorption because this is the refractive index you can see in visible part, except some region over here which has a minor variation between snow and water, which is a sweet short wave infrared region. You have difference, but here it is not at all difference. And neither there is a difference in the refractive index in real part, nor there is a refractive index in imaginary part. So neither there is a difference in absorption, nor there is a difference in refractive. So why? Water looks substantially different than snow.
Because of the granular shape of ice.
Still, you are far away. We will try to explore that, what really happens. Because these are the fundamental questions, and you look at it, how it looks like. If you can look at that high reflector of snow, high visible region. So if you can see the snow, the reflectors of snow, which is in this is visible part of the spectrum, which is very high. And now, as you move towards the higher wavelength, suddenly the reflections of snow comes very down. And there is water in it. Ice, snow, ice. Oh, there is no water. But water will have reflectors like this. It will not drop more than 20%. And why is that? That is an important question. If you can understand that question, you will be in position to apply remote sensing, particularly satellite remote sensing for snow study. And let us look into this issue, what really happens to that. The key to this is, as we were discussing earlier, is key to this problem is the trapped air between the ice crystal. Fundamentally, two things has to happen if snow has to convert it into the water. That means all ice crystal has to melt. But that doesn't make a difference because refractive index in water and ice are same. But one more thing it has to do is remove all air which is trapped between the pores away. It has to enter into the atmosphere and you have a density of water which is close to 1 or 1 defined. So this entire space has to go. So the trick of very high albedo to low albedo is done by this air which is trapped between. And what we really do is then it will, as the incident radiation comes into it, it is changing its little bit direction because of the difference in the refractive indexes, and it will come out, and the moment it comes out, the another ice it will again change its direction because it is coming out from ice to the air, and as it comes to the air, it struck to the another ice crystal, and it stuck to another crystal, again it changes its direction. So as it is multiple changing its direction, it can have multiple scattering, and it is called, then eventually it leads to the forward scattering, and you have very high albedo. So the key to this problem is the trapped air, and that is why, as we remove this trapped air, what will happen? If we remove the 10% of trapped air, what is going to happen? Density will go up. Density goes up, albedo goes down. So it is possible for you to link. What you can do by using remote sensing is you will know the albedo. You can relate albedo with the density. That is why, and density will tell you how much glaciers store water or how much snow stored water is there. So, or whether there is avalanche. So, all these things are done. That is why all these things, density, albedo, are very important parameter when you want to interpret satellite images. And so now let us move into this issue that before going to that slide, just I wanted to show you again this slide and say what really happens to the spectral reflections. See, as a human being, we have very limited vision, that means we can see only up to 700 nanometers, but satellite remote sensing has much larger spectral band, as you can see. And all modern satellites now have a spectral band which is in green, which is in red, which is in near infrared, and we have a speed band which is around 1300 to 1500. So we have now band which has spectral reflectors where it is maximum over here, and you have spectral reflectors around 1500 nanometer, which is very low there. So now you look into this picture and you will see, is there any other object which has this characteristic? That means very high reflectance in visible band and very low reflectance in sphere band. Which is that object here? You can look into the ice, of course, snow, but if you look into the soil, you can see that the soil has relatively less reflectance in visible band. And as we move towards the sea, it has very high reflectance. Correct? Look into another feature, which is vegetation. This is the vegetation curve. And you can see here, it has a low reflectance in the visible region, and it has a sphere region also. If you go here, you can also relate. So in both the region, it has low reflectance. So now we have a unique spectral reflectance characteristic where snow has very high reflectance in visible region and very low reflectance into sphere region. And can we use this characteristic to delineate snow by using satellite images? That is now we are moving to that one, and therefore we will look now another concept which is called algorithm. That means now we want to do it automatically, we don't want to do manually all the time. We want to do it by using computers, and so that there is a less human interference whenever it comes to doing this. So what is real algorithm? It is nothing but a method expressed as a finite list of well-defined instructions for calculating a function. And what is the function at this time? Snow. Yeah? We want to detect snow. That is what we want to do. So this is in snow, and this means the instruction should be unique so that it can estimate snow from other land features and vegetation, rock, soil, and water. Because any given land will have numerous features. That is vegetation, rock, soil, and water. But we want to detect the snow. And in snow cover extraction algorithm, pattern data should be used band or with a combination of band so that it can have a unique range. Now just think that why can't we use only one band? Or can we use more than one band to do that? So many times you will be thinking is, what will happen? Because visible band are very high reflectors, and we can use only visible band. Why do we require another band, which is a sphere which has substantially lower reflectors to do that? Or another thing is, can we use the DN? What is the meaning of DN? So, what is the difference between DN and reflectors?
Calculate albedo from DN. Calculate from albedo we can calculate from DN.
Where do we calculate?
What is DN? What is DN? What is DN?
Digital number.
You can calculate this calculate.
Okay. All of you know digital number, what it means? Yes, because many of you have already said that you know the process. That is first thing you need to know is the digital number. What is it? This is the number which is what essentially you get from satellite images in the pixels, and the pixels have number, and that number is the number, and we have located to that. So let us look at. We have just I wanted to show you that you have a very high reflection in visible region, and you have very low reflections in sphere region. Correct? Clear? Now you look into the satellite images, how it looks like. This image is in visible region, and this region is the sphere region. And the region where reflectance is high looks high, and region where reflectance is low looks completely dark. That is why reflectors are important. You got the point? Now we want to exploit this unique characteristics of snow for delineation and to say how much area in the basin is covered by seasonal snow. Another story, if you want to know the albedo, is another story. If you want to know water equivalent, it's another story. Not all stories we are going to explore today, but let us explore one story, that how much is the aerial extent of snow. Once you know the aerial extent, and the next step is, if you know the density, you will know what you will know. If you know area and density, what you will know? Yeah, you will know the water equivalent, and if you link with albedo, then you will be able to say how much is melting and how much water it will produce for some more time. So this is the link. We are not going to explore all link, but we are going to explore the first thing is how much area is of snow. And why it is a complicated and difficult. On the surface of it looks very simple, but when you start doing it, it gets complicated and difficult. The first thing is you need to plot it and say that what really happens. That means you manually or any other way you try to identify different features and you plot it. That means this is the x-axis, you have a green band, and y-axis you have a field band. And this is the reflectors. If you are plotted, you can see here that you have a cloud over here, you have ice over here, and then snow over here. So you can see here they are scattered throughout the one. So if we have some potential to separate between the rock is here, vegetation is here, and so they have a potential to separate between reflections provides us opportunity to separate between the different landscape and different features. So this is what it is all about. The next key question is, when you are going to build any algorithm for you, important thing to know is the sensor parameter. Because how that image is acquired. How many of you have seen the satellite images? Okay, good. Wonderful. So I don't have to go into detail of that. So if you have, now let us understand, because your perception from satellite images may be something which is written in the books and on how it is, say, into the header file. But what it is in reality in the ground? let us look into that. First, we have first key question of any parameter: what is its spatial resolution? That means how much surface of the line satellite can see, and which is known as spatial resolution. Correct? So now you have if you take the AWIES, how many of you have seen the AWIES data? Which satellite data you have seen? I'm saying AWIES, which satellite? List. What is the spatial resolution of list code? 500. Okay. Close to that. So now when you actually start building the satellite, now this. So what is going to happen is you have one CCD which is going to measure certain amount of distance. So that is instantaneous field of view, what it is called. So that is never unique. Let us look into this. It has across the track. What is the meaning of across the track? If satellite is moving this way, perpendicular to that. Okay? And it had 56 meters near Anil. What it means?
56 meters.
So you will suppose this is satellite and this is line, and here it is 56 meters. That means minimum area it can map. And if you go 70 meters off Nadi, that means if it is basically this much distance from this to this, so this is 70 meters at this end. So what you will do? Because if you, many of you have seen satellite images, it says only one special resolution. It doesn't say different special resolution. Correct? So you do something else to it. Just keep going. And top of that, along the track, that means as it is moving, it has another special resolution. So it is across the moon, across the track, and along the track, as it is keep moving, it will have another special resolution, which is 66 meters. And the integration of time is 9.96 milliseconds. If you look into the any satellite engineering model, spatial resolution is always given in the time. And what it means? What it means is suppose satellite has some altitude from ground, which is around 900 meters, and as it moves, it has to acquire reflected from the ground. Either it should transmit it to the ground, or it should record it. And if you fail to do that within 9.96 milliseconds, you are going to get gaps. That means satellite is going to move into another area, and it is not going to acquire data from next step. So, as satellite moves from this position to a further position, it should have already transmitted the data from first position towards the ground station and taken the next satellite and taken the next reflection. If it doesn't happen, you will have a gap. And it is a function of, and how much time it will have to do that. In this particular case, it is 9.96 milliseconds is the time which is available satellite to do it. And it will then determine how much land it can see. So that determines its spatial resolution along the path. So it is 66 meters. So you have now three different spatial resolutions on three directions. One direction X, direction Y, and then three directions on the ground. You have a three or each pixel will have two, one is x-axis and one is y-axis. It will have two different spatial resolution and it will vary from pixel to pixel. So sometimes x will vary from 56 to 70 and y will remain constant as 66 meters if y is along the track. So what it means, you need, and if you really look into that, what people will normally say is 56 meters is the spatial resolution of every step. What means entire data has to be resampled and each pixel has to be generated in the spatial size of 56 meters. And what it means? It means you are going to change its geometry. So what you are actually going to see on the reflector on the ground need not be that 56 by 56 meters, but this something else got mixed into it. So you have to understand. Everybody got to clear out this concept. Or anybody has confusion. This is very important. When you are going to use satellite images for some purpose, people will say that I take one pixel and say something on that. My experience demonstrates that people will take a group of pixels because they are familiar that one pixel has some contamination from surrounding pixel because of the resampling. Is it clear? Or still there is confusion this time? Okay, so now we will move further. The next important thing is the smart. That means how much this distance, how much it will see. Right? And this is 740 kilometers for AWIES sensor. We are not talking about the AWIES sensor, only one sensor of AWIES. So you can see here, it is 740 kilometers distance we can see at a time. So what it means? Suppose instead of 700, how much is swath of least sensor? And you have to do the least ghost sensor, but how much is swath of this for?
25 kilometers.
This 25 close to that, and not 25 is this 4. And less than that, you can say, and how much is swath for this 3? Something like, you can say 1600, whatever. And this is 704. What it means? How it will affect your studies? No, we are going close to that. What you saying? Okay. So you require additional correction. But why this is important?
Covers
More geographical area. True. In one go.
and you can more resolution.
Okay, there are two things done because of this. One thing is, as you take a longer the swath, the curvature is fine, and you require correction for curvature. You require a special resolution because, see, number of how many CCD, because that concept I will not talk about it. Number of, because you have because it's a charge coupled devices, which is like not our ordinary camera, which has satellite camera, it has the same thing, which has a charge coupled devices, that is small CCDs are there. Correct? And which looks at the specific region along this path. So suppose you have fixed this number. Technology allows us how many 500, 400, whatever it is. You have fixed this number is fixed. And so what is going to happen is, if we distribute this for 700 kilometers, if the spatial resolution will be 700 kilometers divided by each pixel will have. Correct? Because we don't want to miss any land. Correct? And if we reduce the swath, say to 15 kilometers, then what is going to be 15 kilometers divided by the same number of, so you will have better spatial resolution. So spatial resolution is a function of swath. Correct? You require the intervening optics to take care of this thing because you require different focal length and other things. But that is another engineering. But it has some other implication as well. What it means is your ability to visit the same line feature significantly reduces more as you have less and less swath. Correct? So you have this swath which is 700 kilometers. You can see the same line feature at the interval of 5 years. And if you have this with this 4 data, which is a 5 meter, you can visit it once in a couple of months. Even there are tricks on that where you can steer the satellite, but you can steer the camera. But if you are not steering the camera and looking at down, it may take a couple of months for you to come to the same line feature. So these are the trade-offs you need to make depending upon what you want to do. Suppose I want to study how seasonal snow is changing. If I come and revisit that area after 2 months, then there's not snow is completely melted away. The wet season started, if you start in May and sometime you come in July and August, by the entire snow is melted, so your study is meaningless. So you require that where we have very high temporal revision. So we have to work on that like 700 meters per slightly reduced. Suppose I want to study glacier retreat. And glaciers are retreating at the rate of 10 meters or 15 meters per year. And that is retreating and they come annually. So even if I revisit that space after 1 year, that is good enough for me. But they are retreating very low rate, therefore I will need a 5 meter special. So I will use these 4 data if you want to study glaciers. So your decision of which satellite data you are going to use depends upon what you want to. So that says all these features are important for you to understand. Now this another key parameter is quantization. What it means?
The number of pixels per image.
No. What is this quantization? Please tell me. Yes. Okay, that is true. Just Google it and see. Even though I will answer it later on, but I will see this is very simple. Simple thing quantization, which is used in a bits. So another key is linear setting. That means this is a crucial parameter in any interpretation is because all electronic systems will need to decide up to what maximum extent it will really record the data. And suppose it is linear setting is given it is microwatt per centimeter square per stereo per micron. What it means is if it is received the 53 band 2, if it receives the 53 microwatt energy, it will be recorded as a 53. And if it receives the 54, it will record as a 53. So anything above 53 will be recorded as a 53. So this is a saturation limit. So if you have a line feature which is reflecting energy more than 53 microwatt per stereo per micron, then it will record as a 53. So you will have saturation. And what it means is you will have no ability to detect enough no reflectors if it is more than saturation limit. So this is very important because many times if you see the history like that, you will find that all they are getting large mixtures of saturation. So you need to understand that, and this is normally done at 100% albedo in this AWIES diagram. The 53 over here, then band 2 is 47, band 4 is 31.5, and band 5 is 7.5. That is 100% reflected. That means it is equivalent to the incoming solar radiation. So now the important question is, will there is still saturation? What do you think? Is it possible, if you use this satellite sensor, AWIES sensor, is it possible that we can still have a saturation? Even though our saturation limit is equivalent to the incoming solar radiation. Think of it. I will not answer, I will leave for you to think of it. Or maybe I will answer in between somewhere. But think, this is very important for you to understand when you start going to do more and more scientific research. What is going to happen? Now we will now move a little bit further because we already know that there are two different bands of the electromagnetic spectrum where we have very high reflectance of snow and another band which is mean which has very less reflectance of snow, and we can use it and make an index of it, and which is called normalized difference snow index, and we can use the reflectance of AWIES band 2. And you can use the reflectance of band 5, and you can really get this index, and which is called normalized difference snow index, which is commonly used now. It's almost done to do that. But the important question is it unique? Because now as we move towards that, one of the key questions which I have already asked you: can you use the DL, digital number? And here I am talking about the reflectors. Is there any difference between these two? Think of it. We will discuss this later on. But these are the questions which you need to understand or ask yourself if you want to do it. But first important thing for you to know is wavelength and reflectors. How that reflectance and how much is NDSI. This work was done in Manali in 20 observatory, where we have estimated spectral reflectance of different land features. You can see here the pine, you see here wet snow, high rate snow, water and cloud, and you can see here that where from the data, but we can see here if you look into pine and different band, and if you look into NDSI, it has a negative NDSI. The forest will have a negative NDSI, the very high NDSI around 0.9, and cloud has 0.2 NDSI, and water is the only land feature in this terrain which has an NDSI which is close to snow. So what it means? So it means that if we have an algorithm by using NDSI, it is possible that we can identify water as a snow. Correct? So we need some other trick or some other scientific, scheme to remove water from snow. Clear? Is it clear or still confused? So what will happen? The questions which I asked you earlier is, Even if you have a satellite sensor with 100% saturation limit, then the sensor can still get saturated. Or 100, if you have 100% of incoming solar radiation, it is possible for the sensor to get saturated. But before answering this question, we need to understand what we see in the satellite. That means once solar radiation comes from sun, what really happens to that? It moves through the atmosphere, correct? And as it moves through the atmosphere, there is scattering. That means energy gets scattered into the atmosphere, and depending upon which region of the electromagnetic spectrum you are, and some of that scattered energy is moving upward and reaching to the sensor. So you have extra energy, which otherwise would have come from land, is also coming from atmosphere, and which is called path radiance. Correct? So that is one source. Then what happens is, as it comes on the surface, it gets reflected. However, the reflection is not isotropic. It will depend upon solar radiation angle and the orientation of the surface. Some of these issues we will discuss when I go to give exercise day after tomorrow and see those issues. So it will depend upon numerous things, and which is called as bidirectional reflective function. That means if it is not completely level to the surface, that means it will vary from angle. If you have this angle, it depends upon hemispherical angle. Depending upon angle, its amount of reflected staging, that means the energy which is reflected back is function of this hemispherical angle, which is called bidirectional reflective function. Then it has to transmit to the atmosphere, and then it reaches there. So, whatever you see on the satellite, it's not necessarily only because of the energy which is reflected by surface, but it is also additional thing which is related to satellite. So therefore, we require different corrections. To do that, if you really want to work quantitatively, that means we require a descent scheme to remove this path radiance, that means which is coming from path. We require a descent scheme to address the variation which is called because of the topography, and we will require descent scheme to decide how bidirectional reflective function is going to change. So all these things get complicated and difficult. We will not go into detail of that. But what will be the easiest way? Now I want to convert this digital number, which is a function of quantization, and which is a 10 bits in this case. So 10 bits in how many pixels will be there? How much? 2? Okay, that's all right. Number, at least you have a mathematical expression of that. So now there is the simplest way to do it is the estimation of radiance from digital number. Because what you see on satellite image is the digital number. Now you need to convert that digital number into the radiances. And what is that process in any instrument is called a calibration. That means anything you observe in any instrument, you need to calibrate it and you need to convert this into the desired parameter. So this parameter here is the radiance, how much is that? And this is done in a laboratory itself. That means you can do the digital number. This particular case is either 55 or is 3 or let's say 10. So you have plotted this digital number versus this L minimum arrangement, that means radians. So you plot this graph, and by knowing which is the digital number, you can convert it into the radial phase, and then you can use by DL is the GL P, the simple mathematical relationship you can use, and you can convert this into this form of equation where you know this minimum, this maximum divided by number of DL numbers, 255, DL plus you add this into that, and the bias or calibration coefficient set off. So you can add that. So this is a simple equation which is used. All of you must be using in doing that. Either you are doing it knowingly or doing it unknowingly. Because everybody uses, converts this into this. So this is how you do that. But there are certain issues which I wanted to tell you. When you start building this algorithm, there are, because I given to this, I am talking in the context of everything, but there are certain critical things which you need to know about numerous other. That means if you then look into numerous satellite sensor, you will see here that in a numerous, you take the GLACIER sensor, which is many of you are very commonly using, and you can see here is even though in these three sensors you have very high 185 in the validation, you have 14 in a band 2 in the microwave per centimeter per stereo per micrometer. And you can see here, this one, you can see the difference between these two. But this is at 36% of radiation. What it means? It means is whatever incoming solar radiation, your sensor gets saturated at 36% of that incoming radiation. So you are getting 10 microwatt of energy, sensor is saturating at 3.6. And why is that? What it means is, in most of the flow features, this sensor is going to get saturated. And any change in albedo, you are not going to get by using satellite images. So this another parameter which you need to critically evaluate is the saturation limit of the sensor before you start using it for snow study. And why this done is another problem. I will not go into that, where we used to have a lot of argument when I was still in ISRO and pushing hard to raise that. And when this sensor was designed, I was the one who was critically involved in designing the instrument, and subsequently we are able to shape it up. You can see here, this is done in 19 and this is done in at the beginning, at the end of around 1990 or 2000. The sensor was launched in 2004. So you can see here that this is substantially raised. And what it means now, this is 100% albedo. So it is 56, 53, 47, 31.5 and 7.5. So you can see for this identical, almost close band, how much is difference in the saturation radius. The 14 is 53, it is 50, it is 47, it is 16, 31, and this is 2.4 to 7.5. So now we have a sensor which is not saturated in snow or in Tuesday. It can still saturate. So what it means is, and this is possible because we have raised because this is 3 is a 7-bit sensor and it has 128 digit number, and AWIES is a 10-bit sensor and it has a 1024 digit number. What it means? Why any designer will do this? Think about it. And understand what is the meaning of dynamic range and why. How you design satellite or satellite sensor is also depend upon what you want. And if you want to study vegetation, dynamic range and saturation limit. And if you want to know what it means. Because radiation has less reflectance and snow has very high. The relationship between the reflectance, dynamic range, and saturation limit or density. This to be understood. I'm just giving you a thought. I will not answer all these questions, but idea is to provoke you to think more. So that you will do that. Now, next thing we want to do is convert these radiance into reflectors. And how do we do that? It can be done very simply. There is not, don't worry too much about this only one ratio. It's not a big value. That once you develop this, so what you have is reflectors of a pixel in a particular band in the Earth's distance in astronomical unit, then mean solar exact atmospheric spectral radius, the solar is angular degree. Remember, this is the same time. This is not elevation. And this means if surface is not perpendicular to the radiation, then the radiation per unit area is reduced by cosine of solar incline. Why is this there? Because what we are saying here is you are giving your Eastern. What that Eastern means? Eastern means solar exo-atmospheric spectral irradiance. And how it is? So if you have sun radiation coming like this, sun is here, the radiation is coming, it is perpendicular to this. But it is not necessary all the time. Surface will be perpendicular to sun radiation. And if it is making angle, any angle, then its footprint will change. And that will cause change in irradiance, and means that relationship is a cosine relationship. You can look into the numerous papers which derives this thing and how it is derived, and there is one of my papers where it was derived published 15 years back. You can look into that. And you can see here what it means. It means that if it's changing because it's a question of theta s, which is a not, which is the angle which is making, and as it makes the inclination, then new angle is added to that, and which is causing change in incoming solar radiation per unit area. Per unit area, remember that. And that relationship is a cosine relationship. So we need to know, what we need to know here is, we need to know how much angle land surface is making to the thing. What is the angle of sun which is making to the thing? Because depending on which time of year and which place on the land, if you move from equator, if you move towards the polar region, this angle is variable. So all those things you need to understand. And then you can make the correction for incoming solar radiation, not for reflectance. That you also understand. So what is the bottom line of the story is? These are complex things. If I want to convert DA number or into radiance in one step, but I want to convert radiance into the reflectance. These are complex things. That means I need to know how much bidirectional, in how much reflectance is changing in hemisphere, that is bidirectional reflecting function. I need to know how much angle it is making to light, how much I should know about the sun characteristic. So it is a complex business to convert radiance into the reflectors. So can I have any method by which I can avoid this state? And I can convert digital number or radiances into product, which is the smoke over area. That will simplify my life, and I can do work which is much more quickly and easy. So we will explore that. That each time when you do the science, you want to avoid doing complex science and make it as simple as possible and as quickly as possible, because your objective is to know the area extent of snow. Your objective is not to find out what is the albedo. Now, this is all about what we are talking. So now look into that. So what will happen? If you look into the issue, what will going to happen? If you have a surface which is northern facing, or surface which is a southern facing, and if you have a different slope, just because of that cosine relationship of incoming solar radiation, you will have a large variation in difference. You can see if it is anything, if it is, suppose if it is northern facing, and if it is a slope which is varying from 10% to 40%, you can see that how reflectors is going to change significantly depending on slope. If you change the direction and the slope remains same, how reflectors is going to change quite significantly. This is just apparent reflection, and this is much error in it. So you can see that it is very, we need to do something more if you want to work on reflectances or if you want to know the albedo. But can we do something to estimate the area extent of snow and do that? And one of the key things we have looked into this is this experimental setup we did in Lundi, and we have done this work to understand how it will change. And you can see here that how the reflectors keep on changing from 0.6% to 79%, 62%, 40% to almost 90%. However, AWIES is not at all changing. Correct? You see, there are large variation in reflectors here, large depending upon slope and orientation, but there is no variation in AWIES. Correct? So what now? It means now we have an index where we need not consider changes in solar elevation, solar zenith angle, or topographic. And it is possible for us to have a unique index where it is independent of topographic local illumination angle, if I call it. All this term together called as local illumination angle. And we change the solar zenith angle, topography, and its relationship with sun and geometry between the earth and sun, or local land surface and sun is called as this angle. So you can see here local illumination angle. So it is independent of local illumination angle. So now we can use NDSI to do without converting DN into reflectors or reflectors into local illumination. And you can see here, it is plotted, and you can see that how you can have a different land features where it is a snow over here, then snow under mountain shadow, over here then there is the water, over here the clouds, fog, rocks, vegetation. So you have somewhere around 0.4 as a boundary between snow and non-snow. It is possible to delineate snow. If NDSI is more than 0.4, you are having snow. If it is less than 0.4, it is any other feature, in which we are not interested to differentiate that. However, still we have water, which we were discussing earlier, is still irritant in our method. So you can see that how it looks like. And the key question is In the two things you can do is what happens to the mountain shadow. That means if you have a big, as we have seen earlier, one side gets illuminated, another side is shadow. Why? In mountain shadow also, you have high NDSI figure. Is there anything shadow here? No. No shadow. Somewhere it is. There you can see under the but just think about it. That why you have, if there is snow in mountain shadow, why it has more than 0.4 ADSI. So what it means is that you have ability to detect snow in mountain shadow also, which otherwise if you use any supervised classification you will not have that ability. Correct? So let us look at these images. What you can interpret from these images? This is this B1 data, band 1, which is visible band of electromagnetic spectrum. So what do you have? This is what you can see. This is November, this is January, this is March, and this is May. What you can interpret? Okay, then one thing, anything else? One thing, just look at it, how it looks like. One picture is in November, one picture in January, another picture in March, third picture in May. What it means? Different seasons. And the season is different. It means you have different solar elevation activities. And if you have different elevation, how it is reflected in these images? Yeah, just look at it. You have here this black patches here, completely vanished. What it means? It means shadows. That means mountain shadows, depending upon solar elevation, as we move towards summer, significantly. Earlier days, people used to have this technique to know whether it is snow or non-snow, depending upon mountain shadow, but you can have still a situation where shadows are vanished. So it is important for you to understand this thing that, of course, you can. So what it means? It means that if you use the ordinary supervised classification, which many of you are familiar, even if snow area is less per se, it's quite possible in January you will interpret less, and in March you will interpret higher, even if snow area is same, depending upon shadow. So this kind of issue you need to understand. What it means now, I have explained it right. This is visible band, this is real band. Why is it the snow? Well, you know the difference in tone of snow will be different to reflectance characteristics. This one is which band spectrum? And this? So you can see that how reflections can affect all this thing. And what is this? For some, everything fails. Suppose you have done reflective study, everything you have done, and still you get very abnormal snow color. This is the last resort for you to look at the satellite images and say whether it is a cloudy or whether it is not. And that you can see, this is taken on the same day, you can see here that how this region is, you can see characteristically clear pattern of valleys and mountains are completely missing and suggesting it is cloud. This is the last resort for any worker if you really want to bring some reasonable results to itself. So that's all what I want to say. And the next, again we will do more time. So we will start our discussion on glaciers. So before that, if you have any questions, you can feel free to ask.
You asked how the snow, water, and ice all at same steady fraction. How is it separated?
Okay, snow, water, and ice. We have no potential in NDS. I cannot be used to separate between snow and ice. Okay, so they are clubbed together as one feature, snow and ice, as one feature. Now the question is how to separate between water. We cannot club them together. Correct? So we have to find some other. So what is that? Some other mechanism. Suppose we take that 2-3 ways by which people have tried to do it. I have tried to do it. Look into one of my numerous papers in 2000. When was that? 5, 6, 7, 8, something like that. The series of papers which I did when this AWIES was launched in 2004. Where I have argued is that how to do it. And it is a function of what kind of policy decisions you want to take. So the other question is that you have a Himalayan region where you have a water body, correct? You go and identify this water body before onset of winter. So you can clearly identify the water body. And when you actually run the algorithm, if you come into that geographical area, you can say this much land area is because that is one. That is one way of looking at it. Another way of looking at it is that water body is anyway going to get fills. And there will be then snow on ice because we have ice which is frozen, on top of that there is snow. So would you consider that is snow or not snow? That is another decision you need to take, and it is very tricky to take because it depends upon what happens to that snow when it melts. If you are interested in estimating runoff, and if you have a relationship between, say, change in snow area and water release into the stream, because that is called, normally what it is called is, what is area altitude curve or something like that. No? There is some typical term for that. And so that water is not going to come into the stream, that water is going into the lake. So whether you want to use as a part of snow cover or not, it again depends upon, will depend upon what purpose this product you want to use. But if you look into the numerous algorithm, where if the water body is frozen and if there is snow on it, many people have used it as snow. And if it is not, suppose you have a large geographical area and still you have water body which is not frozen. Okay? And there is standing water. Like what you have in a pond. If you are doing it for part of the basin, you have just a pond in the back, which is never frozen. And you have every chance classifying this as snow. You can add numerous tricks to it. First thing you want to do is a direct reflection in near infrared band. Near infrared, there is a huge difference in reflection between near infrared band of water and near infrared band of snow. So you can do that also. That would be, I have not actually shown you the flow diagram, but you need to plug into flow very differently, smartly to do that, so that you can differentiate in that by using them by these differences in various lines. That's one way of doing it. The easiest way to do it is remove water body when there is still snow and when water is still in liquid form. Delete it and then subtract. Any other?
Then about this optical image based estimation. What about synthetic and sugar based imaging?
We are not basing that. That is another ball again. Because I can't cover this in one lecture. But it has some application, it has its own limitation. Optical remote sensing, that microwave remote sensing has its own issue to handle. So, that is what.
Usually for it only is
No, you cannot say. It depends upon situation. If you are working in east, where polar regions or eastern Himalaya, where region is very nearly cloudy, you have very little potential to use optical data. So there is nothing called, but processing of microwave data is very complex. And therefore, and then entire video study cannot be done by using microwave because that region is not at all so it depends upon what you want to do. Suppose you want to know what is the effect of black carbon, which is we have not talked about, not that we are going to discuss all issues. Something I will say in the next lecture. We cannot use the microwave because only visible region of the electromagnetic spectrum is affected because of the black carbon. So if you want to know the effect of black carbon on snow melt or glacier melt, we have to stick to the region. So microwave, but if you want to know what is the density, probably you need to move to the microwave which can be affected. So it depends upon what you want to